Hi everyone. So we are doing the first lesson in this unit. The zero's the hero. Technically it's the fourth lesson, but it's our first lesson. All right. And if you take a look at this on our left was our do now. So do that now if you did not, who are not in class. And our learning targets are going to be connect the characteristics and behaviors of quadratic and cubic functions to their factors, as well as determine the zeros of functions and the multiplicity of the function's zeros, and show how linear, quadratic, and cubic functions demonstrate the fundamental theorem of algebra. So we'll talk about multiplicity. That's going to be our keyword today. And fundamental theorem, well, we'll talk about that too. All right, if you take a look on the left-hand side, all of these, remember you're using the zero product property. Well, the first one is linear, so you just solve for x. And the second one, remember you set them both equal to 0 and then solve for it, like how you would in Algebra 1. And the answers are right there for you, so please make sure you check that. If you did not do that in class, because maybe you were multitasking, pause, try it. Okay, because it's one thing to be like, oh yeah, but if you actually try and do it, you're like, oh, wait a minute, what are we supposed to do again? How are we doing this? It's different, so try it. All right, moving on to the next ones. If I can scroll down. Okay, here we go. So a couple things we did here, just as a quick reminder of a degree of 1, which means that the highest exponent on a polynomial is 1. So like this first one right here, that's what we call linear. And if the highest degree is 2, then it's quadratic. The highest degree is 3, then it is cubic. Good. If you should have notes on that. That was earlier in Unit 1. I'm pretty sure it's Unit 1. So again, we'll talk about that in just a little bit. But if right here, we just found the zeros. So since we found these are linear, and we found x is equal to 0 here, just set these equal to 0, right? So x minus 1 is equal to 0, solve for x. Same thing, just like how we did for the do now, right? And these we noticed were quadratic. How did we know that? Because if we were to multiply this out, the biggest exponent would be x times x, which is x squared. Same thing here for e, it's x times x, which would be cubic. So it's x to e, x to the third power. All right, and then and if you notice right here, some of these would come out twice, right? Here we have x minus 1 is equal to 0, and another x minus 1 equals to 0. So technically we have x equal to 1 and 1. So there's 2 of them, right? And if you'll notice the purple, we're not there yet. All right, but we just solved for that. And then we look down here and we talked about multiplicity, right? So the multiplicity is basically how many times a particular number is a 0 for a given function, right? So how many times does it happen, right? So if you notice right here for f, 0 happened 2 times, right? So we call that 0 mult 2. So in other words, 0 multiplicity of 2, and then just 1 because 1 only came out once. And if right here we have 2 1s and we have a 0, right? So we have here 0 and 1 multiplicity of 2. 1 second, I'm going to sneeze. Nope, it's gone. It's gone, it's not here. Again, here is 1 multiplicity of 2. So how many roots do we have here, including multiplicities, right? So here we do have 1 here as a 0, and then 2 as a multiplicity of 1. So there are 3 roots altogether. So notice for a cubic, it has 3 roots. For a quadratic, it has 2 roots. And for a linear, it has 1 root, right? And notice, so in linears, you'll never see multiplicities. That's why in Algebra 1, you never talked about it because there's no such thing. I guess a multiplicity of 1, but we assume that. So if we don't write down multiplicity of 1. So anything bigger than 1, that's what we're going to put in. And note, you can never have like 0.5, 2.5 multiplicities. Like that doesn't make any sense, right? It can't come out like half a time. So this is what we call the fundamental theorem of algebra. However many degrees it has, that's how many roots it's going to have, whether real or imaginary. Because as we know, some of those roots in a quadratic can be imaginary, right? All these ones we have are factorable, so obviously they're real, right? But they may have imaginary roots. So that is the fundamental theorem of algebra. 2 degrees, 2 roots. 5 degrees, 5 roots. Okay, so that's how you can tell how many roots you're looking for. They may not all be real, but there's 5 of them. All right, moving on. So we're going to do a whole bunch of skipping, skip, 1, 2, skip a few. If you want to take a look at them, it's quite interesting because it literally does decompose the cubics. So if you were taking a look at this one right here, the g of x right here, the x plus 2, that's linear. 3x minus 2, that's also linear. And x plus 4, that is also linear. So if you multiply 3 linear binomials, what would you get? You would get a cubic. That's what you end up with. You end up with funkiness, right? So this is just, well, how do we change this to look like this guy right here, right? And so what I would do is I would practice that. If you're a little uncertain, you're like, ooh, do I know how to do that? And try it. Either you could do it doing distributive, or you can use the box method. Either way is okay. Okay. And then just make sure there's no shortcut way. You just have to multiply the first two binomials, and then whatever you get after that is usually a trinomial. Then you just multiply with the other binomial. There's no other way. You just have to multiply it all. And then check to see if you get the same answer, which you should. All right. And then right here, we just found the zeros and then we plotted them. And then we went on Desmos to see if we could see what that actually looks like. In this class, we're not going to be too concerned about how high or how low they are, the mins and the maxes, right? Just like how we had for quadratics. But I do want to know, you're going to have to show me that you know how to find the roots and the y-intercept. And also the arms, but we're not getting to the arms today. Okay, so the roots we know how to do, right? Because, let's just set everything equal to 0. And so x plus 2 equals a 0. Negative 3x plus 2 equals a 0, right? Do you see how we put them all equal to 0? Solve for them. So we get these 3 roots. So negative 2, 2/3, and negative 1/2, right? So I just put them in. I went each box, I went 2 boxes is equal to 1. That's what I did so that it's kind of more spread out. It's not so small and tiny. And I put them here. And then my question was, well, what's the y-intercept? It's the same thing as if we were to do with a quadratic, right? The y-intercept is that plus 4 right there, right? Because if remember, well, the y-intercept is when x equal to 0. Well, if x equal to 0, all these are zeros. All we have left is the plus 4, right? So that's where my y-intercept is going to be right there. All right, and then we're going to go to Desmos. I have that ready for you. Remember, this is how we check. So this is what it turned out to be. So remember our roots here, -2, -0.5, and that remember is 2/3, right? 0.6 bar. And then our y-intercept is here at 4, which we knew. And so we're looking at the arm. So the arms are from on either side of that graph. The arms are going up and goes down, okay? And that's what we drew it just like about that. Was that exactly right? Now that's okay though. But you just need to make sure that it's going down here and then coming up through, and it's going through these points, right? And then same thing with this one. We found I would practice this, try this, pause it, do it. All right, and then our roots we found were to be -2 and -1/5, and we drew that in here. And this was not a very good drawing, so I apologize. That's going to be my point right there. My y-intercept we know is 2 because once we multiply it all out, that last number here is 2, or the shortcut way is, well, this is 2 times 1, which is 2. That's how we get this last number, right? I technically don't care about this other stuff because it doesn't tell me anything right now. I just want the y-intercept. So that's what you could do. Same thing with the last one right there, or this C right here. This was really bad. This was a bad drawing. So I just did this here, right? So this is what it should look like. Oops, so again, your roots are going to be here at negative 0.5 and 1, and y-intercept is at 1 as well. So that's what that graph looks like. When I'm asking you to graph these things, I want you to do them by hand, not to look on Desmos and try to copy it down. That's not what I want, okay? And then right here for D, this is, remember, it's cubed, which means we were literally going to do x plus 2 3 times. If you notice, I did it 3 times here. This is supposed to be a 0. Sorry, it looks weird. And so our answer is going to be -3 multiplicity of, or -2 multiplicity of 3. What does that actually look like? Well, it looks like that, as you can see. But if you notice right here, I'm going to just, that's right, oop, come on. So do you see how it kind of looked like a parabola that was broken? So one of the arms were broken and went down like this. So this is right here at the root. This is our point of inflection right here. Okay. And notice if I had it without this, right? Ooh, and turn it on. This is what it normally is, just x cubed. So if it's x plus 2, right, notice what happens, right? Just moves. And which makes me wonder, well, what if we made it, instead of that, we make it plus 3? What's going to happen? See how it moved over? So it's now 3 away on the x-axis. Weird. This has to do with transformations, which you guys won't see until pre-calculus. You would have normally seen it here, but we're kind of on a tight schedule, you know, COVID and all. Sad days. Okay, so that is that. Let me move on. Okay, so that's what happens when we have multiplicities of 3. When you have multiplicity, it doesn't make you wonder what happens when you have a multiplicity of 2. You kind of already know because you've kind of already seen it. Want me to show you? Okay, I can just change this to a 2. So that to a 2. Oh, not to that kind of 2. Let me try that to a 2. See? That to a 2. Ah, blah. Let's try this again. That to a 32. There we go. Well, cool thing about decimal is that you can just kind of tinker around with them. This is what happens when you have a multiplicity of 2. Crazy, huh? And if I were to add something in there like x minus 1, now notice right here, still bounces off. And then it goes through 1. See, multiplicity of 2, this is what happens. Quadratics happen to them. It's like that part is like a parabola type. Okay, so anyways, moving on. We're going to learn more about that later. Okay, so Max was like, well, x plus 2 and to the third power is equivalent to x cubed plus 8. Why is that not the same? Why is that a thumbs down? Because remember, what this means, x plus 2 times x plus 2 times x plus 2, which is, and Max forgot that whole middle part right there, right? Because you're doing a whole bunch of multiplication. Nothing cancels out because they're all pluses. So nothing's going to cancel out. So that's what that looks like. That's why it's wrong. And so if you look at B right here, it says how many x-intercepts does the function x plus 2 cubed have? Well, it has only one x-intercept, right? Here at -2. But the other question is, well, how many zeros counted with multiplicity, right? That's 3, because it's a multiplicity of 3. So if I ask you how many roots does it have? 3. How many x-intercepts? 1. Got it? Make sense? Okay. All right. Now for the talk, I said we would do this. So let's do this. We have a few minutes here. I would recommend that you pause right now and then hit play. Serious. Okay. So then I'm looking right here, and this is going to be, I'm sure you now are pressing play because you've done this already, and you're just going to check. So if you notice right here, we're going to look for our roots. So it's x plus 3 is equal to 0, negative x plus 5 is equal to 0, and 2x, nope, just kidding. 2 minus 2x is equal to 0. So here, x is equal to, if you're subtracting 3 on both sides, it's just going to be -3. This is a little bit tricky. What I like to do, if I see that this is a negative x, I just add x instead. You know what I mean? So then that cancels out, and all I have left is 5 is equal to x, which is the same thing as x equals to 5, right? Because honestly, okay, let me show you the other way. This is the way that most people do it. I just don't like it. It's just too long for me. It just has an additional step. That's all. So normally we subtract 5 on both sides, but notice it's negative x is equal to -5. Well, if the negative of x is equal to -5, then well, what is x equal to? And you're like, I don't know. And then you're just going to you can just divide by -1. I like to multiply by -1, but either way. So this is going to be x is equal to +5. See, same thing, 5. So I just like doing it this way. I just make that x, I make it positive at all costs almost. And same thing here. So do you see how the negative is with the x? So I just like to add the 2x on both sides. And I like dealing with positives. because I'm a positive person. I get rid of the negative. So deep. Divide by 2 on both sides is x equals equal to 1, right? So we have -3, 5, and 1. So we're going to go 1, 2, 3. Here's -3. Here's 1. Oh, I should probably put a dot there. Try to make them the even spacings. My spacings are not that even, but I'm trying. Try my best, I promise. So here's 1 right here, and here's 5 right there. All right, there it is. And it says label the zeros. Ooh, we could even find out what our y-intercept is going to be, because if I take all of this, just the constant numbers, that's going to be 3 times 5 times 2, which is 30. That's like huge. So I'm going to just be like 30. Boom. Okay, and then what do we do? Well, we know the only 3 places it can cross the x-axis is here. It will never cross anywhere else. So if I start from up here, I'm not going to be able to come back up to meet this 30, right? It's not going to happen for me. So what I'm going to do, I'm going to have to start from down here, go up here to 30. Let me try that one more time. It probably comes up like this because it's usually symmetrical-ish, and then comes down and comes back up again. Cubics look like this. Cubic always looks like awkward. One arm up, one arm down. Looks like one of these guys, okay? All right, there we go. Okay, and then so that's the only way it could work. If we try to do it the other way, if you notice, so if I try to go like this, I'm like, well, I can't cross the y-axis except for here. And I can't get back up there unless I cross the x-axis, but I can't cross it until 1. So therefore, it's not, I can't, do you see how I'm stuck? I can't do this, right? So the arm has to be going down, or you have to use your logic just a little bit. Okay, so try the next one. Well, we kind of know this one already, remember? So this one is going to be x minus 2 is equal to 0, and we know it's x equals to 2. And how many times that happened? Oop, not comma. Multiplicity of 3. So we're going to go over here, 1, 2, boom, just like that. That's 2. Should probably label that. What's my y-intercept? It's just going to be -2 cubed, right? Because we're going to multiply -2 3 times. That's going to be -8. So we're going to go down here to -8. It's going to cross. Now remember what the multiplicity of 3's look like. Multiplicity of 3's either look like this or like this, depending. But here it looks like we're going to go down and then up because of where my y-intercept is. Ooh, that looks kind of okay, but there should be a point of inflection right at that too. Okay, that's what it is. So how are cubic functions similar to linear functions? Well, they have an x-intercept and a y-intercept, right? And what else? They have arrows at both ends. And how are they different? The cubic ones curve and the linear ones don't. And cubic ones have 3 roots, whereas the linear ones only have 1, right? And how are they similar to quadratic functions? Pretty much this, they both have x and y intercepts. They have multiple roots. Cubics have 1 more than the quadratic, right? You know what the quadratics feel like the cubics are? They're like, I always feel like they're trying to one-up me. Because the roots, anyways, I won't explain. And yep, there we go. And that's the end. I will talk to you guys later. Bye.